So I talked last time about Carnot vapor power cycle. I'll speak a little bit more about it. Why? Because it's the gold standard, it's the benchmark. And if you really understand the Carnot vapor power cycle, I think you're better prepared to understand the Rankine vapor power cycle. So last time we introduced it having 4 components. You should be able to sketch it by memory: boiler, turbine, condenser, pump, and the states, and then describe it. So let me do this. We have a choice. I'll give you a pop quiz right here, right? So A, B, C, or D. And what I want to know is where is the condition of the fluid saturated liquid, and where is the fluid saturated vapor? For answer A, you would say it's at 1 and 3, or 2 and 4, or 4 and 1, or 1 and 4. Of those choices, which one is state 1 saturated liquid and state 3 saturated vapor, or which one works? Okay? For the Carnot vapor power cycle. And your choices are A is 1 is saturated liquid and 3 is saturated vapor, or B it's 2 and 4, or C it's 4 and 1, or D it's 1 and 4. All right, we'll all done? All done. What do you mean 1 second? You can't say all done and then 1 second. I'm stopping at 60 seconds. All right, we are completed, and now we show the results. So it's very nice to learn that most students know that state 4, right up here, is saturated liquid, and state 1 is saturated vapor. True? So C was the correct answer, and we press forward. Well, this is named after, the Carnot vapor power cycle is named after Sadi Carnot, but there's his full name, Nicolas Leonard Sadi Carnot. These are the years that he lived, 1793 to 1832. You do the math, he lived just a month or two over after his 36th birthday. He didn't live very long, right? He was born in Paris, France, and he lived in Paris, or France. He only wrote one book, one memoir or a book, okay? It was published in French, but I can't read French, so the English translation is Reflections on the Motive Power of Fire. Reflections, he's just thinking, on the motive, how you translate fire into motion, lifting, turning things. Burn something to turn something. Burn something to lift something, okay? So the motive power of fire. And he had 2 main points. One, he didn't do a lot of math in it. You can read it today. It's been reprinted for many, many years in Dover Publications and probably other publishers too. Translated into English, and you can read it. I don't strongly encourage it, but if you're interested, there's a cover of one of the translations. And 2 main things without a lot of math. He said, I think that the efficiency of our engine, heat engine, is a function only of 2 temperatures, which are the reservoir temperatures between which it operates. It has to ingest some heat and has to dispose of some heat, and it tries to convert as much of the heat that it ingests into work. That's our heat engine. So he thought, hey, it's only a function of those. You can have all these complicated processes and everything else, high-level abstraction, and it's true. That's how the science eventually worked it out, that the thermal efficiency is only a function of the low temperature and the high temperature in an absolute temperature scale. Also, the maximum efficiency obtainable does not depend upon the exact nature of the working fluid. Can I have a Carnot cycle with air? Can I have a Carnot cycle with water? Can I have a Carnot cycle with refrigerant? And all of them still get the same thermal efficiency? That is really a shocking result. That's why it's still talked about to this day in thermodynamics, and that's why you see his name all over. You can go to Wikipedia, look at his picture, you can get more information. Here's a TS diagram. Did I show it to you last time?
No.
This is plotted in MATLAB, and it's used calling ref-prop. This is true to scale plot for steam. And it's a temperature entropy diagram. Take a look. What's the low temperature? 0. Here's 100 degrees C. Water boils. The boiling point, atmospheric pressure. What's up here? 600, 700. It's hot steam, right? It's rare that you have steam applications way up there in an operating power plant. They push the limits, but it's metallurgical considerations that often limit the maximum temperatures. Okay, the thing has to hold together and work for a number of years without falling apart. And then entropy, it's hard to interpret the values there, but that's what it is, increasing order, disorder. Now, another opportunity for a question. This point right here, is it A, the critical point, or B, triple point, or C, other? So we'll turn it on and we'll collect up. We'll stop at 30 seconds. What's the name of that point at the top? Critical point, triple point, or another name? Let's go ahead and stop. And we'll collect and show the results. At the critical point, that's very good. So 81% are correct. This is the critical point. It's not the triple point, okay? That's at the top of the dome. Let's ask this question. This is another question. This line that goes from the critical point in increasing S but decreasing temperature, that's a line of either A, saturated liquid, or B, saturated vapor. I'll turn on the question. Take your responses. We'll definitely stop at 30 seconds or earlier. This is a confidence booster. This is to see if I could get 100% correct at least once. All right? We are done. Stop. And then show results. Oh. Why do I have 4% that are thwarting my efforts? Okay. It is saturated vapor. That's the sequence of lines going down. Let's close this out. And all of these, I'm going to go for 100%. I'm going to go for 100% here. Either these are a line of saturated liquid or a lines of saturated vapor. All right, next question. We start. All right, we're about ready to finish off here. And I'm ready to stop it before the wrong answers are guessed. I stop. I show results. There's always one. Okay, now take a look. What happens if I would say, is it possible to have the entropy a value of 2 and the temperature a value of 400? Nope. Not in any serious engineering application. You just can't have willy-nilly any combination of pressure and temperature and entropy and other values, okay? How about this? If I said the entropy was 8 and the temperature is 400, right? You could go out and say, oh, I think the pressure's around that value, okay? It's out in the, what region is this out here? Let me ask a question. Okay, you got it, superheated. Otherwise, it's a quicker question. But it's superheated vapor, right? And then where is the region where it's subcooled or compressed liquid? All confined right in here. Very narrow band on a temperature entropy diagram. Very narrow. Do you mean, Professor, that MATLAB tried to plot all of these blue lines all down in here? Yep, that's why it just looks like a big thick wad of blue lines. Let's go ahead and take a look at the plot here. I can try to zoom it in, and then I can try and move it down a little bit, and you can see that, yep, there's a whole bunch of those lines coming in. Let's solve a problem. Water is the working fluid in a Carnot vapor power cycle. The saturated vapor enters the turbine at 8 megapascals. So it's 8 MPa, and it's saturated vapor. I'm going to say that the condenser pressure is 20 kilopascal. All right? And saturated liquid enters the boiler. Saturated liquid. Property values are in the table that you're going to construct, and I'll show you on the next page. But you would construct a table where you would have state 1, 2, 3, 4. And then you would probably put some property values like kilopascal for pressure. And temperature, maybe in Kelvin or degrees C. And then you would start listing them, okay? So here's a quick clicker question. Answer A, B, C, or D. What two pressures are the same? Is the pressure 1 equal to the pressure 2? And the pressure 3 equal to the pressure 4? Or is pressure 1 equal to pressure 3 and pressure 2 equal to pressure 4? Or is pressure 1 equal to the pressure 4 and the pressure 2 equal to the pressure 3? Or is pressure 2 equal to the pressure 3 and pressure 3 equal to the pressure 1? One of those answers is correct. I will start and give you sufficient time to answer that question. You're in? You're already in. All right, we're done. Let's go ahead and stop. And let's show the results. Congratulations. Look at that. This is a harder question, but, you know, that's pretty good. So you can fill in the pressure column right away. Could you not? So right away, you could put in 8,000, 20, 20, and 8,000. All right. Now that you got the pressure down like that, switch them all. Maybe I won't make it that many. Which temperatures are the same? Is the temperature 1 equal to the temperature 4? Is the temperature and the temp, I don't know. I'm trying to make these up as we go. Let's do this one. And the temperature 2 equal to the temperature 3, or C, the temperature 4 equal to the temperature 3. I'm going to stop there, and I'm going to say select, I haven't turned it on yet, select the incorrect answer. There's 3 answers. Are 2 of them right? Yeah. Which one is incorrect? I start the answer. There you go. You're selecting the wrong answer. You're selecting the wrong answer. Which one is incorrect? And we show the results. And C is the incorrect. Does that mean that the temperature at 1 is equal to the temperature at 4? So this T, is this equal to this T? And how do I find it? It's the saturation temperature at 8 megapascal, is it not? If you look it up, it's around 295 degrees C. All right, just a shy bit under 300, 295. And that these two temperatures are the same in the condenser, the inlet and outlet to the condenser? Yes. And how would I find it? Saturation temperature at the 20 kPa. All right, another question then. Is temperature at 2 greater than 100 degrees C, equal to 100 degrees C, less than 100 degrees C, or don't know? How the D ends. So that's A, B, C, and D. Hopefully you understand that question. So I'm going to turn it on. And now we're on. And I want to know if T2 is greater than 100 degrees C, equal to 100 degrees C, less than 100 degrees C, or it cannot be determined. Don't know. It can't be determined. I don't know. You know, you have to give me more information. Then I could tell you. That's answer D, if you like that answer. D. Okay? All right, we're about ready to stop. Last chance to throw your answer in the hat. You ready to answer? Check it out. I'm going to stop. Done. All right, now we show the results. Well, we have a distribution. Let me ask you this. If this pressure was 100 kilopascal, or 101.325 kilopascal, what would be the temperature at 2 or 3? If it was precisely 1 atm, what would be the temperature? 100 degrees C. So it's at a lower pressure. It's at 20 kilopascal. It's at a lower temperature. The boiling point is lower. So the correct answer, C. Did the explanation help? So this comes in right around 60 degrees C and right around 60 degrees C. All right. Now, there's a couple other columns of interest that you might want to have in a table like this, but eventually we're going to have enthalpy and entropy. Kilojoules per kilogram and kilojoules per kilogram Kelvin. Yes, sir?
Where did, for state 2 and state 3, the pressure at 20 kilopascals, where did that come from?
I didn't write it in the problem statement. I said it verbally that the condenser pressure is 20 kilopascal. Okay. And when I show you the table on the next slide with all the values, it will show the 20 kilopascal that I intended to write in the problem statement. Make sense?
Yeah.
All right. Any other questions? So we want to be able to get the enthalpy and the entropy. Well, we go ahead and remind ourselves on a temperature entropy diagram, this thing fits on the dome, does it? And you pegged at the high pressure line, this is the high pressure line, and this is the low pressure line. You peg state 1 and 4 in the corners. Where did you put state 1? Saturated vapor, right there at high pressure. What's state 4? Saturated liquid at that high pressure line. You're going to do the best turbine, reversible. It's also well insulated. It's adiabatic, it's reversible, hence it's isentropic expansion. It's a straight line down as well as a straight line up through the pump. 1 to 2, straight line down. State 3 to 4, straight line up. All right? Then it goes across and across. That's your whole cycle on a TS diagram. So let me ask you this question. S1, is it equal to S2, S3, or S4? Answer A, B, or C. Is the entropy at state 1 equal to the entropy at state 2, equal to the entropy at state 3, or the entropy at state 4? There we go. I opened it up. All right. I think we're all in, so I'll go ahead and kill it. We'll stop now. Stop and show the results. Very good. That the entropy at state 2, you can just see it from this diagram. They have the same entropy. S2 is equal to S1. So the answer is A. Now, I'm going to try real hard to get 100%. Okay, now the other question I have is, if I was going to evaluate S1 numerically, do I have enough information on this table to get it? Yes or no? I need some more information. A or B? I start. I have enough information on this table to get S1. Yes or no? Stop. Now we show the results. I'm going to have to learn how to expose people. Okay, it's how do I find it? Let's do this one. S1, is it going to be equal to S of G at M8 PA, less than SG at 8 MPa, or greater than SG at 8 MPa? Answer A, B, or C. I turn it on. All right, we're about there, right? So let's go ahead and stop. And then we show the results. I'm going to get 100%.
You think so?
So this is S of G at 8 MPa. It's the saturated vapors entropy. Well, all right, now we're going to have a little time. I'm going to shoot for 100%. I want to get H at 1. Is the enthalpy at state 1 equal to H of G at 8 MPa, less than H of G at 8 MPa, or greater than H of G at 8 MPa? I press the go. I start to collect responses. All right, we're done. We stop, and then we show results. I'm an educator. All right, now I just move on over to that one, and we're done. Congratulations. That's right, at 8 MPa, and then 8 MPa. Now, what about state 2? This one's a little more tricky, so I'm going to ask this one carefully. I want to know the enthalpy at state 2. Is it equal to Hg at 20 kPa? Is it less than Hg at 20 kPa? Or is it greater than Hg at 20 kPa? I start. I'm going to stop. All right, let's show the results. So B, which says that H2 is less than the saturated vapor enthalpy at 20 kPa. It's true, right? It's not superheated, right? And it's not saturated vapor at 20 kPa, right? So B is the correct answer. Does that make sense? So how do I find this value at 2? How do I find H2? Do I first need to calculate maybe quality at 2? Yes. And how do I find, okay, let me ask you this question. How do I find it? Let's do it verbally. Forget the clickers. How do I find X2? S1 is equal to S2. It's isentropic expansion such that, let me ask you this, is X2 equal to S1 minus S of F at 20 kPa divided by S of G minus S of F at 20 kPa. Both of those are at 20 kPa. It's at the pressure, 20 kilopascal. Does that look good? That's how you get the quality. True? Once you got the quality at state 2, because this S is equal to that S, S1 is equal to S2, then you can calculate H2. How would I get H2? Would it be equal to H of F plus the quality at 2, H of FG? Yes or no? Yes, it would be. Okay, let's take a look. Can I get, what would be easier to get, S of 4 or S of 3? Which one would be easier to get, S of 4 or S of 3? 4. Because it's on the line. It's saturated liquid at the 8 megapascal, so it's a lot easier to get 4. That's equal to S of F at the 8 megapascal. Once I know that, then I got S3. S3 is equal to S4, true? Would I then go and get, okay, how about this one? Is it going to be harder? I'm going to ask a clicker question. Here's a clicker question for you. Answer A. It's harder, more work, you understand, harder, more work to get H4, or it's harder to get H3, only A or B. Let me turn on the thing. I have to get H4, and I have to eventually get H3. Both of those I have to get. Which one is going to be harder? H4 harder or H3 harder? Wow, that's great. There you go. So what is H4? This is H of F at that. H3, I've got to get the quality at 3, knowing the entropy and interpolate. And then I have to get H3 just like I got H2, knowing the quality. Okay. Once I have all of those, can I calculate the work that the turbine produces as a positive out? What is the equation? H1 minus H2. Okay. Now this is where it gets a little tricky. The positive direction for the heat transfer out of the condenser, the heat transfer is positive out. QC is positive out of the condenser. I want the equation for that. Is QC equal to, and here we'll do the clickers, is it going to be H2 minus H3 or H3 minus H2? Answer A or answer B? Show the results. Well, it looks like most people said A. What is larger? Is H2 greater than H3? It is. And we're talking about a positive heat transfer out. It is A. It's H2 minus H3. Now, let's do the work into the pump. Look at the direction of the work, WP. It's not out of the pump, it's into the pump. So is WP equal to H4 minus H3 or H3 minus H4? It's a positive work of the pump I'm looking for. It's a positive value. True? There we go. Well, let me ask you this. Which enthalpy is greater, H4 or H3? H4 is greater. Why is H4 greater? Because I just pumped some energy into the fluid. All right. So it's H4 minus H3. I got these enthalpies in the table. Okay, then you would use those to calculate the work and the heat transfers. How about the Q into the boiler? And this is into the boiler. QB into the boiler. What's the equation for QB? Is it H1 minus H4? How many people like that? Thumbs up? Good. Yeah, thumbs up. Now that I have all of those heat transfers or work transfers, I can calculate a metric of interest, the back work ratio. It's the percent of the work out of the turbine that has to go back and feed the pump. That's the back work ratio. The other performance metric is the thermal efficiency of the cycle. The thermal efficiency is the net work out. Well, it's the turbine out minus what had to go back and feed the pump. That's the net work out, divided by the heat transfer in, and only in is in the boiler. So that's Q sub B. True? Somebody said, Professor, you just studied the Carnot vapor power cycle. I learned that the Carnot vapor power cycle has a thermal efficiency that's 1 minus the low temperature over the high temperature. So I would take this high temperature, add 273, because I don't want to make a mistake and not put in degree. I don't want to put in degree C for TH. I want to put in Kelvin for TH. And so that's TH. All right. And then I go and get TC or T low. That's 60 plus 273. And I put that right here. And I put that right there. Is that going to give me which one of these thermal efficiencies is going to be greater? They're going to be the same. Now, I asked this at the 8 o'clock. And I said, how many people did a calculation in Thermo 1 or even so far in your studies at Thermo 2, and you did all of the calculations for a Carnot vapor power cycle, then you did the simple little equation for the Carnot, and you compared them, and they were the same. How many people did that so far? Only a few hands. You really, everybody. Now, everybody, who's going to do that? Yeah, there's all the hands up. You need to do that. And if you remember the first time you do it, it's surprising how accurate it is, isn't it? those that did it. It's like, hold it. I went all this elaborate work, and then I have this very simple equation, and they give me the same answer. That's sometimes startling. So here's the problem solved. I will just show you. I added the specific volumes, flow exergies, have the state, dead state. You see that 295 to 60. You see the percent quality. I forgot to put the percent quality in here, but it's around 33% or so. All of the enthalpies, entropies. Notice that these two values of entropy are the same. These two values of entropy are the same. I even put a little descriptor of how the states are fixed or calculated. For the dead state, temperature and pressure, fix it. Oh, it's pressure and it's saturated vapor. Pressure and entropy, pressure and entropy, pressure, saturated liquid. Calculate the work of the turbine, calculate the Q of the condenser, the work of the pump, the Q of the boiler, the net work, the back work ratio, and the thermal efficiency. This back work ratio is way too high. 31% of what comes out of the turbine has to be devoted back to this quote-unquote pump. This thermal efficiency agrees with the 1 minus TL over TH, where you put in Kelvin. Okay? All right. Let's show it on that temperature entropy diagram. Well, the Carnot cycle is simply a box, a rectangle. The Carnot cycle goes like this and around. Okay? So you can see it's at 8 megapascal, 20 kilopascal. Is all of the heat brought into the Carnot cycle all at this high temperature of around just a shy bit under 300 degrees C? Is all the heat brought in at that high temperature? Yes. Is all of the heat rejected at around 60 degrees C out of the condenser? It is. Okay, so it's isothermal on the heat addition and isothermal on the heat rejection. That has to be true for a Carnot cycle. Somebody says, you know what, why do you peg the corner right here? This was state 1. Couldn't I put state 1 right here where it had the quality at state 1 is 90%, not 100%? And could I move the quality at state 4 going from here to right here, so that the quality of state 4 is 10%? Could I run that problem too? Would I get a little rectangle that looks like this? Right? And if I did that with a smaller rectangle, somebody says, I want to know, is the thermal efficiency for the original system, the bigger system, the one with the corners at 1 and 4 on the saturated, liquid saturated vapor line, is that going to be, how is that going to compare with the new one, where I moved the corners for 4 is now 10% and 1 is now 90% quality? Is this going to be the same? Is this going to be greater? Or is this going to be less? Answer A, B, or C. Everybody in? All right, we'll call it stopped. Show the results. Let me ask this question. Is all of the heat transfer, if it was this new system as shown like here, all right, is all of the heat transfer coming in, is it still all at the same TH? Is all of the heat transfer out still at the same low T low? 1 minus TL over TH. Did that change? So the correct answer is B. B is the correct answer, is it not? All right. Who wants to really be, I mean, this one is if only if you're a gold A+ student can you get this one right. So we just ask it for fun. What was our other metric? Back work ratio. Back work ratio of this new system with the corners pushed in, okay, like that, versus the back work ratio of the original system. Is the back work ratio the same? Or is it greater or less? So answer A, B, or C. Of this new system where you push in the corners, what's the back work ratio do? Turn on. Now we'll start taking your answers. What was the backwork ratio before? I forgot, Professor. Oh, it was around 31.5%. That's what it was originally. Don't worry, this is a very tough question. How about a hint? I'll tell you this. The backwork ratio on this new system, when you push it in and push it in like that, comes out at 41.2%. You can change your answer if you like. I'll keep it open for a second or two longer. But I have to shut it down sometime, so I'm going to shut it down now, okay? So let's stop it. And do you think everybody's going to get the right answer? 41% is greater than 31%. Okay, so let's press forward. So now the next one is a modified. Did I introduce the practical Carnot vapor power cycle? We called it the Rankine cycle. After this man right here, here's this picture off of Wikipedia. His William John Maruquin Rankine, or Rankine, okay? What years did he live? So these are the years he lived, 1820 to 1872. When you get older, you start looking at this. Oh, no. Guess who's older in this room than 52? Oh, that hurts. That hurts. That hurts. And he is from Scotland. Everybody knows where Scotland is, I hope. Don't tell me if you don't. Right? Had a wide range of interests. In 1943, he published a paper on the fatigue of metals in railroad axles. Very important in 1843. In 1855, the Queen of England, Victoria, had a chair and gave him the chair in civil engineering and mechanics at the University of Glasgow, Scotland. In 1859, he produced a manual on steam engine and other prime movers. So right there, and that's why we honor him with the name Rankine Vapor Power Cycle. He's also the Rankine behind the temperature scale, and there's also a continuing lecture series in geomechanics. So this person really did a lot in science and engineering. Now, this state will still leave to be saturated vapor, but we're going to move the saturated or the liquid. So is the saturated liquid state, is that state 2, state 3, or state 4? Answer A, B, or C. Which state now for the practical Rankine cycle, or the practical Carnot, known as the Rankine cycle, has a state which is saturated liquid? State A, B, or C? And we'll show the results. Well, what comes out of the condenser? If the condenser works really good, it doesn't put out something that's partially condensed, and then you put it through the pump like the Carnot. That really is hard to do. So if your condenser works really well, it condenses all the way, and what comes out? Saturated liquid. Saturated liquid. So before we had state 4 was quote-unquote saturated liquid in the Carnot cycle, but that's not practical. This is very practical. Saturated liquid is at state 3, so B is the correct answer. And then you have much less work to drive the pump. The pump takes a lot less work to boost the same pressure to go from 20 kilopascal to 8 megapascal. It's a lot cheaper. A lot less work required per kilogram that goes through the device called a pump. A lot fewer kilojoules per kilogram that goes through the pump to boost the pressure, the same pressure difference. Okay? Here is the cycle 4 states shown on a TS diagram. Whereas what state is shown right here at 8 megapascal and saturated vapor? State 1, that comes out of the boiler and into the turbine. What comes out of the turbine? It's still a great turbine. It's reversible expansion, straight down to state 2. Okay? Then, instead of condensing partially and then stopping and going up, we condense all the way down to state 3. Okay, Professor, I see the state 3 is a little circle there, the black circle. Where's state 4? Right there. There's 2 circles shown in MATLAB. I don't see them. Well, you have to blow it up. And when you blow it up, and I mean really blow it up, they have the same S, and one is on a line of 20 kPa, and one is on a line of 8,000 kPa, or 8 megapascals, see? And this is still the temperature scale. So you tell me, estimate visually, what is the increase in temperature from state 3 to state 4 for this pump that's really going to do a great job? It's reversible. What's the increase in temperature? How many degrees C increase in temperature? It's about a third or a half. It's not even 1 degree. To take it from 20 kPa to 8,000 kPa, that's a huge pressure change. Now, if you had some irreversibilities, well, then the friction in the pump, and then you say, does the pump heat up, then heat up the air, or does the pump heat up and then heat up the water that goes through the pump? That's a question you can deal with later. But for the perfect pump, it really comes out so slightly hotter. It's insignificantly warmer, okay? Well, with that, I'm done for the day. Thank you for your attention and your participation.